A child finishes a bowl of cold ice cream. An hour later, they're running a 101-degree fever. Did the ice cream directly cause the temperature spike, or is the timing just a complete coincidence? When two events happen back to back, our brains immediately connect them. We are biologically wired to find patterns and assume that the first event caused the second. But trusting that gut instinct is a terrible way to do science. To figure out what's actually happening in reality, we have to test our assumptions against a strict mathematical system. Researchers resolve this problem of coincidence using a framework called hypothesis testing. The process starts with a baseline assumption called the null hypothesis. This is the default state of scientific skepticism. In our example, it states that there is absolutely zero relationship between the ice cream and the fever. Opposing that baseline is the alternative hypothesis, the active claim that eating the cold ice cream actually caused the child's temperature to rise. To decide between the two, researchers have to draw a line in the sand. They set a mathematical boundary called a significance level, which dictates exactly how much hard evidence is required to abandon that baseline skepticism. But drawing that line is risky. Real-world data naturally fluctuates, which means wherever you put that boundary, you are mathematically guaranteeing a chance of making an error. Plotting 100 healthy temperature checks creates a baseline cluster around 98.6 degrees, forming a normal probability curve. The father sets a 5% significance level, cordoning off the extreme right edge. The new 101-degree reading lands squarely inside this critical region. Because the new data crossed his threshold, the father officially rejects the null hypothesis, blaming the ice cream. But what if the thermometer is simply broken? The child might be fine, and the father jumped to a conclusion based on a faulty reading. In statistics, this mistake is called a type 1 error, or alpha. It happens when a researcher's threshold is too sensitive. They mistakenly reject a true null hypothesis over a random fluke. It's a statistical false alarm. To prevent a false alarm, the father becomes highly skeptical, pushing his boundary out to a strict 1% significance level. The 101-degree reading hasn't changed, but it now sits comfortably inside the unshaded normal zone of the curve. Looking at this new setup, the father shrugs off the fever as random chance. He accepts the null hypothesis, assuming the child is completely healthy. But here's the flaw. What if the ice cream really caused a mild throat infection? By dismissing the data, he missed a real connection. This is a type 2 error, or beta. A type 2 error occurs when a test is so strictly conservative that a researcher accepts a false null hypothesis. They get a false negative, missing a genuine real-world effect entirely. To measure this sliding scale, scientists use the p-value. This represents the exact mathematical probability of getting that extreme 101-degree reading if the ice cream truly had nothing to do with it. Intentionally pushing the p-value closer to zero actively protects a researcher from a false alarm. But as they do that, they mathematically inflate their risk of a type 2 error. This trade-off is permanent. However, researchers can squeeze both margins of error down at the exact same time by drastically increasing their sample size. Collecting hundreds of new readings naturally concentrates the data, shrinking those extreme tails. But eventually, statistical certainty hits a hard mathematical ceiling. Zooming out from a child eating ice cream, these calculations form the foundation of all medical and social research. Every study claiming a breakthrough in cancer treatments or warning the public about a dangerous new food additive has wrestled with this exact balance between alpha and beta errors. Science is not the pursuit of absolute certainty. It is the discipline of deciding exactly which type of error you are more willing to risk.